So for every x here, then there's also a corresponding point right there. That's the f of that x. So we'll say that that's like x1. That's the f of x1 right there. So this x1 corresponds to this point right there. So that means if we were to take an x2 and x2, it would correspond to this point right here, f of x2. So you can see then how we have like it's just f of x. This function f, it's simply like where it is along that y-axis. So even though I wrote this delta x and delta y, you could really think of this more as like a delta f, because that's really what we're basically saying is we have this point. We'll say x3. We have this point. Let's call it x4. And so then the function right here, that's at x, well, we always do, whenever we calculate the slope of a line, it's always the second, it's always like y2 minus y1 over x2 minus x1, and that always equals our slope m. So in this case, we're looking at we're looking at this as f of x4, because that's like the second point, of x4 minus f of x3. And remember, this is just a fancy way of saying like y2 and y1 divided by, and then we simply take our change in x, simply x4 minus x3, x4 minus x3. And so that's simply the slope right there, this line, the slope of that line right there. Of course, it doesn't actually have, it's like the full equation for a line is y equals mx plus b, right? So we don't actually have that b, but we do have this slope m, so it's to start. And so then imagining this though, like rather than having a set x4, imagining instead we didn't worry about this x4, and instead we were like, okay, so x4 and x3, there's a certain relation, right? x4 minus x3, there's a certain that's a certain change in x. We'll call it delta x. It's some constant. And so imagine then like x4, what if we didn't want to write x4 right here? What if instead we just wanted to keep everything in terms of x3? So we'll just, because the reason will become clear in just a second. We really want to get back this definition of the derivative, which I hope you can see. So we'll just solve for x4, because this is just a nice little equation. So x4 equals, we add x3 to both sides. Then we have delta x plus x3. And so then we come up with an expression for x4, and then what we'll do is we'll just fill that back. We'll just replace this x4 with this expression right here. So yeah, so in that case we'll just have this f of, rather than x4, we have this delta x plus 3. Delta x plus x3 minus f of x3 on top of, we have this delta x plus x3, because that's just that x4 that's coming back from over here, minus our x3. And then, so now this again just equals that slope m, the same slope that we had calculated prior right here. And but then looking back at this graph, what we want to really know though is what happens as, like, rather than taking this large change in x, what if we kind of shifted this point over right here? What if we shifted that x4 to something like over here, and we made that change in x smaller? So now we have this line that's going more like through this point right here. And so there's a slight little change. There's that slight little degree angle change you can see in the line. That's at this point. But then since we're moving this one over, we don't actually need to rewrite anything, like, even though we're going to call this, we're just, all we're really doing is we're making this term, this delta x, a bit smaller, right? Because x4 is now, it's closer to x3. So that means that this x4 is just smaller. So that change in x is just, it's getting a little bit smaller. And so then we'll think about, okay, so what happens then is like x, as that change in x gets even smaller, like as it approaches that actually what happens is as this delta x term, that change in x, as that approaches 0. So like on that previous term we had a triangle that kind of looked like that. So what happens when we make the triangle more like that, and then like that, and when we make it like infinitesimally small, that change in x, and infinitesimally, actually it's the right term for it, when we make it infinitesimally small, then that's the slope the slope is no longer an approximation. Like this slope right here is an approximation of the slope of the line of this curve at that point. And this using this point right here, then this line is also a better approximation of the slope of this curve, or this f of x, at this point. But then as delta x gets even smaller, then the slope of whatever line that we get will actually be equal to the slope of that of this function at that point. And that's really the definition of the derivative. So we're just looking at, so basically what we want to do is we want to make this change in x, because like x4 is represented by this change in x plus x3. So what we want to do is we want to make that change in x even as small as we possibly can. We basically want to make it make it basically 0. So we want to take the limit as delta x approaches 0. And I don't know if you've taken limits. I don't think you're even in calculus. So this is Calc 1 stuff. So if this is all cryptic to you, then you can send me another email, and I can try to describe a different way of calculating a line that's tangent to the parabola, and also parallel to that one. But this is just the most straightforward way of doing it. Just a small review on taking derivatives. So that being said, so we take the limit as delta x approaches 0. So that is going to be the slope of this function f of x. It's going to be that slope at that point. In this case, we're calling that point x3. So then imagining though, say we wanted to find a more generic, like x3. That's an actual number. What if instead we wanted to find the slope for any x along this function? So in that case, we'd just replace x3, like this constant x3, with just generic x, and then so that means the limit as delta x approaches 0 of f of delta x plus x minus f of x on top of delta x plus x minus x. And then that's simply our derivative. We just write it with a little prime sign, f prime of x, and that's the derivative. And so this function then, it describes the slope of this function at every single x. So at any single x along here, you could plug that x in and calculate what the slope is at that point. And we'll try a quick little example. Example kind of helps, but yes, it's literally just the slope. You just think about this. This is simply like a function that describes the slope. So basically the same thing that we did right here with this parabola and this line. We looked like, okay, at this point the slopes were really negative, so we have this really negative thing. At this point it's less negative, so it's a higher y, and then at this point it's even less negative, all the way to like right here where that slope is clearly 0. Like it's a flat, like that's where a point where it's flat. So that's definitely 0. And then as we go farther this way, then the slope becomes more and more positive. So it goes, so like, yeah, we'd have this function then that describes the slope of this parabola at every single x. And this is just kind of the mathematical notation behind that. And so we can actually simplify this a little bit, because I'm working and I see these two x's, they kind of cancel out. So then we're just simply left with f of delta x. I mean, we could keep them in, but it's kind of pointless because we're just going to keep writing stuff. So those two cancel out, and we're just left with delta x on the bottom. So that means the limit as delta x approaches 0. And this is just the definition. That's still f prime of x. This is just the definition of the derivative. You'll find it anywhere. And so so with this being the definition, then we'll go